This is a series on real-time operating systems. I'm Bernie Woodland, and I own the Raging distribution. This time, I'm going to talk about RTOSs versus schedulers. And I've had preliminary talks about schedulers and RTOSs up to this point, and this will be the final discussion. And this time, I'm going to compare an RTOS with a scheduler and show you why you ought to use an RTOS and not a scheduler. Because there's a lot of people out there who use schedulers and they're happy. And they think, why do I need an RTOS? I can do this in a scheduler. Just show me what you're doing here and I'll show you how I can do it in a scheduler. I hear that a lot. So schedule, of course, is a generic term for real-time capable OS, which doesn't fulfill the requirements which I covered in previous parts to this series. It doesn't cover the requirements one or more for an RTOS. And schedulers are simpler than RTOSs, and they are what was running on old 6502, Z80, 6809 type CPUs out of necessity way back in the days when those chips were used for embedded products. So the reason why the people used schedulers back then was because of the lack of computing resources available. You didn't have a choice. When you're dealing with these tiny chips back in the 80s, these microcontrollers that might have 500 some bytes of RAM, 1K of RAM, something as small as that. You only have enough space to put one stack on there, and when you go into an RTOS, you start needing multiple stacks, and those stacks are used to save off registers. You switch back and forth between one thread and another, save off the registers, and it starts eating up stack space. So right out of the gate, they didn't have a choice because they didn't have enough RAM. Of course, they were limited on flash. I should say back then they were limited on text space because they didn't have flash. They had EPROMs, double EPROMs, PROMs, whatever. And those things would usually go up to, they go anywhere from 16K to 64K. That wasn't as much of an issue because you can squeeze an RTOS into a small flash footprint, but the code that went along with the RTOS wouldn't fit. And the other reasons are when you start doing context switching. I talked about this in a previous part. Your context switching can get a little complicated. And things start to go down different code paths of execution, and your likelihood of having a crash goes up, and you don't have the mechanisms to diagnose crashes. You don't have a lot of mechanisms, period. In the old days, you didn't have the JTAG debuggers, things like that. You couldn't attach GDB or something, then step through and set breakpoints, very limited debug capability. So the scheduler was the most simple path that it followed the same path of execution. So the likelihood of a crash was smaller. Now you would get bugs, of course, but you wouldn't get as many crashes. Also, the scheduler is for simple tasks. A scheduler is more efficient as far as CPU utilization than an RTOS. So people that have low power applications where they're not doing much will want that power savings over the luxury of an RTOS. So all these arguments for a scheduler, you'll hear other people make them, and they'll talk about how they've got libraries of stuff that work, and Uh, most of those people who are in love with schedulers have never used an RTOS or haven't used it very much, or they've used it, but they haven't run across the benefits of an RTOS, because the problem with the scheduler is that as your code base grows, as your application grows, the code that the way the scheduler executes becomes more complex. It becomes complex and more complex than the same application that would be coded in an RTOS. And this is the killer here. So when you end up with a code base which is really complex like this, it becomes a house of cards where adding something is difficult, and then you start to run into timing problems because you need to add something, and it's just not, the code just isn't structured to handle it because you've got too much stuff going on inside of a scheduler. Now, usually what applications which are used, and I'm talking mostly in a corporate environment. If you're a hobbyist, you probably don't face these sort of problems. The problems that you see in companies are different than the hobbyist won't run across those things, and a hobbyist just is out to optimize different parameters, is out to do things differently than, say, a company that's, if you're making a refrigerator, a little chip that runs a refrigerator, that's got to go in a product, and you can't afford to have problems in that product. So you start off with a chip, put in the first generation of refrigerators in a given year, and then 5 years later, you've added more and more complexity to this thing. This thing has grown. That first refrigerator might have had a scheduler used and not an RTOS. And as this thing grows, somebody realizes, we'd be better off if we ran this in an RTOS. So what do you do when you have this code you've been using for years, and 5 years later you want to run an RTOS? Well, you've got two choices. You can either rewrite the code from the ground up, or you can just take the code and move it over into the RTOS and have it basically execute the same way it did when it was a scheduler. Of course, you can have a hybrid approach too, where you do a little bit of this, a little bit of the other. And a lot of times in reality, people say, yeah, well, let's just port this code over to the RTOS in the same way it's running in the scheduler form. And as time permits, we will re-architect parts of it. And I've seen companies do this. Sometimes they've been successful, where they actually have gone in there and gradually refactored the code to take advantage of the stuff on the RTOS. But most of the time, when you port something from a scheduler, it's going to look ugly when you try to adapt that to the RTOS. And also when you do that, you've got to remember that this code when you brought it over from the scheduler, it's probably reached the limits of what it could do in the scheduler, and the limits of what you would want to do in a scheduler. I'll correct myself. And so it's already gotten into that ball of yarn, house of cards state. And when you go to adapt code like this and refactor it, you're thinking, nah, I don't want to touch this. It's going to break all over the place. Got next year's generations of refrigerators that are coming out in a few months. We got to get our code ready for this. We don't have time to go and retest this, and we certainly don't want any new bugs introduced. So these are the practical problems that you run across when you try to port when you port code from a scheduler to an RTOS. Now, here I'm showing this typical looking scheduler thread. So a scheduler just runs in a giant loop. It just runs through a loop, goes back up to the top, it delays. There's other ways of doing this. Might not necessarily delay. It You could just wait for it. You can have a messaging system and just wait for a message to be sent. But it is one thread. It is one thread only, and that thread runs round and around and around. And it takes different paths. So you get into what's known as polling here. So you've got to, so the thread will go into this function, let's say foo routine 1, go into foo routine 1 and check and see if there's anything to do there. Nothing to do. It comes out, goes to foo routine 2, checks and see if there's anything to do there, and continues. And the things that are needed to be done, typically you've got flags, global variables which are set, and you've got to go in there and poll this. The schedulers will invariably end up in some sort of a polling architecture. Polling being checking something to see if it needs to have a operation done to it, rather than needing to have an operation done and telling the task or the event loop or whatever that it needs to start working on this. So another problem you have with the schedulers, in addition to the polling thing, is that in the course of polling, you'll enter a function, and that function might require a lot of CPU time to complete. And maybe the function itself doesn't take that much actual CPU time, but some of the I/O that function will do, maybe some of the messaging to some external peripheral or over a serial bus to some other device, that will need to be, that you'll want to wait for completion of that. So I have an example here where you're going through your scheduler and you've got several bytes to write to flash. Now when you write into flash, you're not wanting to break that up. So people will argue in a scheduler, if you need to write to flash, just write in bits and pieces and just loop around until it's finished. But what most people do is they don't want to do that, and I don't blame them, because when you loop around your scheduler to try to write multiple bytes in a string to flash, it's risky. You could have a crash. You just basically want to do that flash operation, finish it, tie it all down. You don't want to be halfway through a flash operation. You want to get through it and hold off everything else. Well, when you do that, it could consume milliseconds, even seconds of time, and your single thread which runs your scheduler, is blocked. And this is what I call thread hogging. So like in this example, write large string to flash, you're writing all these bytes, and that function won't return until those bytes are written, and flash, it doesn't typically have, depending on the flash of course, doesn't typically have really fast write times. So your single thread is hogged and nothing else can execute. So this shows up in, like if you've ever played with an application that will freeze or apparently lock up, or even a computer will lock up while you're doing an operation. I'm sure you go off the internet and you try to access something in a browser, and the entire browser tab just freezes until that resource on the internet or that operation over the internet is finished, and then everything returns. Well, that's the reason why you get that sort of freezing stuff, is you have code like schedulers, single threads, and you've got a hogging going on. So like I was saying, the workaround for this hogging, if somebody were to complain about this hogging, and I'm not going to step through this code, but you can look at it, is basically each time you loop around, you do a little bit at a time, and you've got all these flags to manage this. So you keep the thread running so it doesn't get hogged, and then you end up with this ugly mess here. So compare this slide with the previous slide. You'll see the previous one is a lot simpler. this workaround that you need for the scheduler introduces a lot of complexity, especially when it's, so you might thinking, well, that's not too bad, but you've got to consider this and all of the other code that the thread is executing. And then you got to consider that this might be going on, there might be this type of workaround in various places, and you've got global variables that are set, sprinkled throughout the code. You're checking this, and you get into all these conditions. It's just more complex than what you would have in the RTOS. These sort of bugs, when a code base grows, these sort of bugs are nasty to fix. You keep adding, it's the house of cards, the game that you play. Every person that's got to add the next card is at risk of having the whole thing collapse. So you get developers that get these mature code bases, then they have a feature they have to finish in a hurry. And a lot of times the managers don't understand why it's taking them so long, or why they have to do so much testing, or why it's so difficult to do what appears on the surface to be an easy fix. And the engineers try and explain that I got my back against the wall with this code base. This might appear to be easy, but the way things are, I've got to put this in here and not break anything else. So when you have an older code base like that built on a scheduler and you're adding all these features, the savings that you had in the beginning are gone. And now you're having to do a lot of regression testing. You're faced with these corner cases with bugs. Your product starts getting these bugs popping up in unusual places, and then you've got these kludges put in that end up freezing things. And you've all used little devices like this, frustrating little devices that lock up. This is one of the reasons why this happens. So why do that? So why use a scheduler when you can use an RTOS? Think about these things. I just threw up this last slide for things to consider when you're starting off from scratch. The temptation is to just code this with a simple scheduler, use what we used over here on this project, and don't try to use an RTOS. And we don't need an RTOS. This thing's so simple, we don't need an RTOS. And what you're saying is that this thing will never grow. You will never need features in the future. You're going to refactor your code. So many times people say that, and the reality is it doesn't come to fruition. These promises that you make now, in a couple of years, you'll have somebody in management, somebody in marketing saying, we've got this new product that's just a little, you can't anticipate the future. So you're safer starting off with an RTOS. That way you're not going to outgrow it and have to move from your scheduler to an RTOS. Because remember, like I said, when you go to port that thing from the scheduler, you're not going to get a nice clean port, and you're not going to get time to do it right. So engineers who have to code this thing are driven by those on the business side that look at things from a feature perspective. They don't understand what's in the code. They don't deal with the code. They look at a feature and they just gauge its complexity based on how that feature works, how it looks from a user's perspective, and experience they've had in the past. They don't understand that the firmware software developers' life. They don't understand when they tell them things that they can't do that just don't make sense. Well, we've done this before. Well, this is different because we've got this old code base and it's going to take 3 months instead of 1 month. The time that you thought you would have for refactoring is first of all going to look, the manager is going to look at that and say, okay, you want to spend the next 6 months rewriting this And what is this going to gain me? How is this going to make me more money? What's this? What new product are you working? Are you just, it's just going to be the same product that just does the same thing. It's just going to change on the inside, and they're not going to sign up for you to go off and do that. And if you did go off and do it, there'd probably be some breakages that you'd have to fix, and nobody likes breakages. So why face that porting problem from Schedular to RTOS when you can just start everything on an RTOS, and as the application grows, you've got your foundation is solid, and you can trim down the RTOS for the first port and then start turning on features. This is a much better development model. This being, the year 2020, as I'm doing this, you've got little tiny CPUs that cost less than $1 that you can run an RTOS on. If you can't find an RTOS to run on a little CPU, use NUFR. NUFR, I've got statistics out there for how it can squeeze onto a small CPU. There's no reason nowadays why you can't run an RTOS on a system on a chip which is $2 or less, $1 in quantities. No reason. There's fewer and fewer 16-bit CPUs out there. Maybe I'll grant an exception here. If you've got a battery application, then you've got to go with a really tiny CPU for that. You're really, really pressed for RAM. And I say really, really, I mean like less than 2K of RAM, because I can fit NUFR on 1K if I had to. But even with all those arguments, with the ability to squeeze an RTOS on a small CPU, you get to do your development on a larger CPU, and then make your port or basically adjustments, or turn off your asserts for that tiny CPU target. Do all of your testing most of your testing on the larger unit, and then do the final tweaks on the tiny thing to squeeze it all in. There's better development models out there. There's no reason to be writing scheduler code, or let's say there's no reason. There are a few reasons to be writing scheduler code anymore. Don't listen to those people who are set in their ways and that's all they want to do is use a scheduler. Ask them, how much experience do you have with an RTOS? All those people that say, yeah, do this with a scheduler, that. Ask them what they've ever done with an RTOS. Ask them. So this is the end of my pitch for using an RTOS and not using a scheduler. In the next parts to this series, I'll start getting into more development stuff for things for those who want to learn RTOSs, and that all this up to this point has been foundational and preliminary. Stay tuned. You're going to enjoy, especially if you're a developer, you're going to enjoy what you hear on these parts coming up. So, and I hope to hear from you. And if you can, drop me a line. Remember, NUFR is part of ragingdisk.org. There's a link over there that'll point to the Bitbucket distribution. There's all kinds of stuff out there, documentation, things where you can put into practice what I'm telling you. So, I hope to hear from you. This is Bernie Woodland. We'll see you next time.